you are watching this YouTube video instead of attending class, you might want to pause the video so that you can try these problems. You're filling in the blanks and labeling as alpha, beta, fission, or fusion. Are you guys ready to go over the answers? Not quite. So remember, guys, the arrow is like the equal sign, and the numbers on one side have to add up to be equal to the other side. And so here the bottom number is 88. So what number do we put here so that the bottom numbers add to 88? An 86, because 86 plus 2 equals 88. And here we have a 226. So what number do we put here so these two sides add to 226? A 222. And we look on our periodic table, element 86, it went from radium to radon. And what type of decay is this? Alpha. This right here is an alpha particle. So we know that's going to be alpha. And I just always circle the particles just so that they're easy for me to spot when I'm doing my quiz or my test. Our next problem, we got 92 on the bottom. We got a 90 here. So what number goes here to add to 92? A 2. 90 plus 2, 92. Yep. And then we got 234 on this side. We got a 230 here. So what goes on top here? A 4. And what element is that? Helium. Do we see an alpha particle or a beta particle? Yep. We got an alpha. Now we've got 2 on the left, only 1 on the right. So these two numbers have to add up to whatever we put over here. So 11 plus 4 is 15. 23 plus 9 is 32. I look on the periodic table. Element 15 is phosphorus. Do you see an alpha or a beta particle on the right side of this one? No. So it's either fission or fusion. It's fission if it makes something, if one element or a bigger element breaking into smaller. It's fusion if it's smaller making bigger. Which one is it? Fusion. Questions? All right, last one. Again, we need those numbers to add up to each other. We got a 6 here. We got a 1 here. What number goes at the bottom here? A 5. We got a 10 here and a 0 there. So this must be a 10. And element number 5 is boron. Do we see an alpha particle or a beta particle? We see a beta particle. A beta can be a positive electron or a negative electron. So I just wanted to emphasize that in this practice problem. Any questions at all? Aiden, will you tuck your nose in, please? I can't wait to not ask people to do that. That's something else I'm excited about for the future. All right. So I'm going to assign your quiz then, if there aren't any questions. So go to Google Classroom. Hey guys, will you be quiet in here? There's no reason to talk right now. So you're going to Google Classroom and you're going to take the quiz that is about to appear. And I am going to project the equations that you need, but the other option if you're at home is the link is under Zoom and other important links. There's a link to the equations that you need to be able to answer these questions, but I will project them in just a moment. And when I do, I will also pause the recording and then we'll pick up the recording when we start our notes after the quiz. So the quiz is not there yet. It's almost there. I'm having trouble because stuff covering my screen. Nuclear decay quiz. Faces. Stop sharing. All right. Ah. Move out of the way for a second so I can shoot. Can you guys at home see the three equations? I don't think they can. Hold on. I think they can now. All right. So be quiet. This is the quiz. These are the three equations you need for the quiz. When we are done with the quiz, I will start the recording again and we will go over today's notes. So our notes are on half-lives today, and a half-life is something that applies to radioactive elements. Does anyone know what a half-life is? Okay, you've heard of it though, right? You've heard of things having a half-life. So that's what we're going to talk about today. So a half-life is the time it takes for half of a sample of a radioactive or a radioisotope to decay. So we've been learning how to do these equations that show different radioactive decay. But the half-life is the time it takes for half of it to do that. Hi. Other side of the main commons. Yes, yes. Because in dating fossils, they literally look at how much of the radioactive elements are left. Because what happens in something that's living is it absorbs I need to think, atoms from the environment, and some of those atoms are radioactive, and when it dies, it can't intake any more atoms. But some of you is radioactive, so if you were to die, and we were able to find your bones millions of years later, we can see how much radioactive stuff is left in your bones and figure out when your bones died. And so we can do that with anything that's been living, right? So we can do it with fossils of animals and plants, things that have been taking in stuff from their environment. Yes, sir. No, because our world is radioactive. You breathe in, like you eat sugars that have carbon, and carbon's radioactive. Like, it's not possible. Plants taking carbon dioxide, carbon is radioactive. That's what we're talking about. Yeah. So, and carbon dating is based on half-lives, the half-life of carbon-14 that's inside those things. So we're basic today, but we're going to continue to work with half-lives on Monday and Tuesday of next week. We're going to do a half-life lab, and we're going to do half-life practice. But today I just wanted to get the notes down of the basic steps of how to do it, and that way we'll have them to refer to. So, by the way, so like you just mentioned carbon-14, carbon dating, that's one type of element, but every single element has its own half-life, the own length of time it takes for half of it to disappear. So different isotopes have different half-lives. And we're going to just sort of show how we walk through this. And so I'm going to keep the math really simple. You start with 100 atoms of a radioactive element. And what the biggest misconception about half-lives is it doesn't take 2 half-lives for everything to disappear. It doesn't. Because every half-life, every time a half-life happens, half of it disappears. And then another half, and then another half, and then another half. So we keep cutting the number in half. So it doesn't usually truly disappear unless you were to get down to 1 atom. And that is why there's still radioactive elements on our Earth. Otherwise, our Earth has existed long enough that all known elements have had at least 2 half-lives. But 2 half-lives means it cuts in half and then it cuts in half again. It doesn't mean it's all gone after 2 half-lives. And that's a common misconception. So let's say you start with 100 atoms of a radioactive element. How many after 1 half-life? 50, right? After 1 half-life, it would cut in half, so about half of them would decay, and you'd have 50. How about after 2 half-lives, how much would you have left? 25. We cut it in half again. After 3 half-lives, about 12 and a half. And so on and so forth. So eventually, if something has a shorter half-life, could it have disappeared on Earth, but it was once here? Could there have been enough half-lives that we got down to that last atom, and then at some point that atom decays? Yes. But a lot of elements that have longer half-lives or that are formed from other elements breaking down in their half-lives still exist, and so our Earth is radioactive. The other type of problem we need to know how to do, and again, we're going to calculate this next week. We're going to do a lab on Monday together. For those of you at home, we're going to use the Skittles for that. And we're going, I brought new Skittles in for you guys. So if you guys have Skittles at home, those are your bonus Skittles. And I'll give you Skittles in class too. You already ate your Skittles? Well, the lab is tomorrow, so yes. Nope. Nope. So here's our other problem that we're going to write about today. So it says the half-life of a substance is 13 minutes. That's not a really realistic half-life, but maybe. I'm just going with an easy number to do math. How much time has passed after 1 half-life? 2 half-lives? 3 half-lives? So after 1 half-life, how much time has passed? 13 minutes. Another half-life has happened. How much total time now? 26 minutes. Another half-life happens. How much time has passed now? 39 minutes. So every half-life is the same length, and every time whatever you have gets cut in half. So far, so good? We're going to end it there and call it a weekend. If you have any missing assignments, you should be working on them. If you haven't started your nuclear research, it would be a good idea to do that during the study hall time today. We are down to 2 weeks left, and after that, there's nothing you can do to change your grade. So it is not the time to chill. If you are behind, it is the time to kick it into gear and get your work done. Bye, Zoomers.